Welcome back. We are now up to chapter 6, and I think my ears keep disappearing in this particular background. As I'm making this recording, it is June 21st, the summer solstice, which is the longest day of the year for the Northern Hemisphere, is typically June 20th, 21st, or 22nd, just depending a little bit on how fast or slow we are with regards to the calendar and how close we are to a leap year and all of that sort of stuff. There is a little bit of variation that goes on there. But what we had happening today were live feeds from Stonehenge, which is an ancient observatory for solstice. And what happens on the solstice is the sun comes up between the stones and doesn't cast any shadow, except the live feed today showed us clouds. Just like here in Indiana, I have clouds outside. In southern England, you typically have that as well. So they didn't unfortunately see all that much, but they still had a nice live feed, and I got this picture off the internet from a couple of years ago. So it was on the National Heritage Site. I do, in fact, have pictures of my own from Stonehenge. So I was there last just a few months ago, and this is my own picture of Stonehenge from when I was there. So I invite you to look at things regarding ancient observatories, none of which had telescopes. But telescopes are what we're going to be talking about today. So as we go through, without any further ado, let me try to figure out how to share my screen. I always have to relearn this. Astronomical instruments, there we go. And again, if you are using a different textbook than the one that is being primarily used for a basis here, the slideshows that I tend to use are based on the OpenStax textbook and the Cosmic Perspective textbooks. What I have done over the past 10 years of teaching is I have often blended things together in that I have taken from bits and pieces of the better of their offerings and added some of my own things to it. So if it doesn't completely correspond to what it is you're reading in your chapter in terms of how things go through, it may bounce around a little bit, but pretty much the pertinent information is still here. But I do invite you to read your textbook as well. This, of course, we're seeing behind me one of the more ancient observatories in the world. Here on our screen on the slide is the Hubble, the HST Hubble Space Telescope, which is one of the most famous and newest of observatories in human history. It's celebrating in this year of 2020, if you're watching this video a long time in the future, its 30th anniversary. It was only really supposed to last from 10 to 15 years in terms of its workable lifespan. It got upgraded several times thanks to the now deactivated shuttle program. So when it begins to falter the next time, unfortunately, that will be it. We don't have anything that can go up and service it anymore. But this is an interesting and phenomenal piece of technology, but far from the only one that's up there. And we have a continuing development of observatories here on our planet. This is another of fairly recent observatories. This is the Keck Observatory, Mauna Kea in Hawaii. Certain things you can see right away from the photograph here. You can see that it is above much of the cloud cover. If you're going to spend hundreds of millions of dollars, and that's how much you're spending when you build observatories like that, sometimes into the billions of dollars. You don't want to build it here in Indiana on the ground where we've got clouds right outside my window. Now, you don't want to do that. Also, you want to get up above as much of the atmosphere as possible so that you can minimize the interference from the atmosphere. One of the things you might notice is this white stuff here, not clouds, but snow. But this is on the big island of Hawaii. So why do we have snow? Well, we have snow because as you go higher in elevation, even if you're closer to the equator, you are going to have cooler temperatures. So you can often tell the people who are arriving in Hawaii to go to the astronomical observatories because they'll sometimes be dressed like they should be going to Alaska. Not a lot of people with parkas come to go down to the beaches. On the other hand, if they're down there and they see the sign that says observatory and they say, oh, well, let's go take a look. By the time they get up here on this road, they're probably freezing because they're dressed in typical Hawaiian fashion. When we look at the universe, we can look at it in different ways. We can look at it in visual light. Here's the Orion constellation. We've got Betelgeuse up here and Rigel down here. If we have really good viewing, we can sometimes make out some of the fuzzy patches here in the area of the nebula. When we're looking at X-rays here, notice we've got some really bright X-ray patches. We've got some interesting developments, but we've also got some things that seem to disappear. And then when we look here in the infrared, we're seeing mostly glow from the heat signatures. And again, this area here where we have our nebula is really lit up here. This is a stellar nursery, and we can see through the gas and dust when we're looking at it in infrared. Telescope basically means seeing from far away. So like telephone is phonic from far away. Television is also seeing videos from far away. How far can you see with the naked eye? How far can you see with a telescope? I often ask in class the question, how far can you see with the naked eye? And some people will say 3 miles and 50 miles and other kinds of things. Well, you can see the moon. That's 250,000 miles away. You can see the sun. That's 93 million miles away. You can see Sirius in the night sky. That's 8 light years away. Actually, the farthest thing we can see with the naked eye in the right viewing conditions will be the bulge of the Andromeda Galaxy, 2 to 2.5 million light years away from us. But how far you can see is not just a matter of what you can see, but how bright the things are that you're looking for, and your ability to see with technology. For most of human history, for thousands of years, this is what an observatory might have looked like. Stonehenge and Machu Picchu, various other places on the planet. We have had eyes and brains and writing and architecture for thousands of years. We have only had telescopes for the last 400 years, and a little bit more than 400 years. If we think about 1608, 1609 as the pivotal dates for that. Telescopes can be, at the basis, incredibly simple instruments. When we're looking at our eye, we have a lens. Light comes through the lens, focuses on the back of the retina. Nothing could be simpler. What we have is a simple lens that focuses the light, and that's the basis of telescopes. So what's happening is in telescopes is we are trying to gather more light, and we are trying to focus the light. Those are sort of the two main objectives of a telescope. There are two main types of telescopes for Roy G. Biv viewing. The far simpler one is the refracting telescope, which takes off on our eye design, which takes off on this very simple design. You have one lens that collects the light at the top. You have a second lens that focuses the light at the bottom, and you have the light going down a tube. This is what Galileo had. He had a long tube with a lens that collected the light in the front and a lens at the back of the tube that focused the light along the way. Then we have reflecting telescopes, where we have a mirror which gathers the light. And in general, you can make larger mirrors than you can lenses. And mirrors are better in a couple of other ways as well. Sort of if we're going to sort of weigh the advantages of them along the way. Refractors are easier to use, but reflectors, you have a mirror that's made here. It doesn't have to be quite the same quality as the lens here in the refractor, for the primary reason that the light doesn't go through it, whereas the light has to go through this without any kinds of imperfections or possibilities of it being warped by doing so. Whereas the mirror, the surface needs to be pristine, but the rest of the mirror typically can be of somewhat less exacting standards. along the way. When we're looking at the largest refracting telescopes, the largest one that was in operation until very recently, just about a year or so ago, it went offline. It's the Yerkes Observatory in southern Wisconsin, sort of northern Chicago area. Not the best area for a telescope. You get a lot of light, even 100 miles away from Chicago, that's going to fill the sky with lots of light pollution. But also it's at a lower elevation. You're going to get a lot of atmospheric interference. But it was handy for the people who were using it at the University of Chicago and others who were supporting this. So I am hopeful that someone will rescue it and put it back to use for sort of public relations purposes, if nothing else. You can see how large the tube is by looking at the person down here in the bottom left. And you can sort of see just how large this is. The lens at the top, when it says it's a 40-inch telescope, that's referring to the lens at the top. As you can see, this tube is a lot longer than 40 inches. This person is longer than 40 inches. But that's what the lens is here. So when we're talking about 40 inches, maybe a little bit longer than that there. So in fact, not all that large, but the lens itself would weigh hundreds of pounds, and it would be at the top of this tube, which, as you can see, can rotate all around 360 degrees and go all the way flat to 90 and all the way up to, or all the way flat to 0 and all the way up to 90. So it can go through an entire 90-degree angle curve, and it can spin around 360 degrees. That means that weight at the top is moving around and spinning around. Now, they're not going to wave it around really rapidly, but that can still add to warping and stresses on the tubes. That's why you can't build them much larger than this without going overboard on the way you construct the tube, and then that becomes cumbersome for movement and other kinds of possibilities of usefulness of the telescope. So reflecting tends to be the way to go. The simplest of them is really one that comes to us from Isaac Newton. We have a mirror that collects things. The starlight comes in, goes to a secondary mirror that is just a typical flat mirror that comes out to your focus, to your eyepiece along the way. The secondary mirror here is curved to fit with the primary mirror, and then your focus is actually in the center at the bottom here. I have a Cassegrain and a Newtonian telescope at home, as well as a couple of refracting telescopes. And then we have the Naismith combination of those different kinds of things. So the largest refracting telescope was built in 1897. That's going to be our Yerkes thing here. We continue to build reflecting telescopes in significant sizes. We don't tend to build too many of the refractors anymore along the way. When we're looking for the different ways in which we would collect light, the light is collected in our reflector at the bottom. So the larger that is, the more light we're going to get. And since it's circular, that means you're expanding out by an area. So just simply adding 1 inch or 2 inches actually massively increases the amount of collecting space you have. So the difference between a 4-inch and a 6-inch and an 8-inch and a 12-inch telescope is going to be dramatic. And you can tell that if you try to buy one as well. I think you can probably buy an 8-inch telescope or somewhere in the neighborhood of $1,500 or so. If you just bump right up to the 10-inch, the prices have now gone up to $5,000. If you get up to the 12 and 14 and 16-inch, you're sort of paying $15,000, $20,000, $25,000 for your telescope. And again, the size refers to the size of the mirror in the back there. But big can get really, really big. Here we have a mirror that's being fabricated for the Very Large Telescope, which is being built in Chile. And you can see again the size of our guys down here. Notice very ultra smooth. This is going to be a massive, massive telescope in terms of size, because it's going to have multiples of this mirror that are there. Here we can see a Palomar 5 meters. So again, you sort of take that, multiply by 5. I can't stretch my arms out far enough across. You can see the guy standing in the doorway here for size comparison, and you can the main mirror is going to be in the center here for this one, and for this one. This one's 8 meters. This one is 5 meters across. The instrumentation all around is less massive than this here, and there are different ways of controlling how a mirror goes around, how the light is collected, but notice they are all inside of massive domes, and they all have the ability to open the slat and let things in. These are typically not going to be air-conditioned and heated rooms. You don't want to have the mirrors themselves, or if you're using a refractor, the lenses themselves sort of heating up and cooling down and warping in contrast to what's happening outside. So you typically keep the temperature inside at the same as you're getting at the outside. This is part of the Keck. Again, that picture that I showed you of the twin domes that were at the top of the mountain. Notice we've got segments here. So instead of making one huge mirror, we have smaller segments that are pieced together. And we've got 36 hexagonal segments. Again, here we can see one of them, and we have a guy in the middle for size comparison there. And we've got 2 different observing platforms so that we can chain them together and use that in interesting ways. We'll talk about those ways here coming up. This is the top of Mauna Kea. Notice there are several different institutions here. When you find a good spot for astronomy, you typically do a lot there. A couple of different reasons why this is helpful. One, the big island of Hawaii doesn't have Los Angeles right on its doorstep. Some of the observatories built in Southern California in the early 20th century now suffer from huge amounts of light pollution. That is not likely to happen on Mauna Kea anytime in the next, say, 25 to 50 years, if even then. Also, this is at a high elevation. It is above a lot of the clouds. It is closer to the equator than you can get pretty much than anywhere else in the actual United States. And because it's closer to the equator, it can see more of the sky over the course of the year. Because if you're by the poles, you can never see the opposite side of the sky. But if you're near the equator, you only have to wait a couple of months before you'll see different sky and different sky and different sky. And over the course of the year, you would see the entire sky. Now, this is not at the equator, so there's part of the southern hemisphere it's missing. The thing is, down in Chile, which also has an area with high, dry, dark desert areas, no big cities, it's on the other side of the equator from Hawaii in terms of latitude, so it can cover the parts that Hawaii can't cover, and it's missing parts of the northern sky that this will do. They are continuing to build on Mauna Kea. There's a bit of a controversy there. I perhaps shouldn't be dismissing it by saying a bit of a controversy. That's just my linguistic mannerisms. There is a controversy that's going on there because this is considered to be a site that is holy or sacred to some of the native Hawaiian islanders. And when things were originally built here, there was a situation where it wasn't always done in concert with the wishes of the people who were native to this. And when one of the later ones was built, it was actually built with the understanding that no more would be built up there. And then there was more being built there. So there's controversy going on about honoring and respecting the wishes and the rights of the people who are indigenous to the area here. And there are various compromises that have happened. This isn't the only place that's happened. There's another place elsewhere in Hawaii for other observatories, and there have been similar controversies, and things have smoothed out. So I'm hopeful that they will be able to continue to work mostly in peace here. But it is important as we build facilities like this because when you build things, you're also destroying things. To build one thing is often to destroy something else. We need to be mindful and respectful of that. So as we look at the way telescopes work, remember we have bigger being better in terms of light collection. The larger the mirror, the more of the sky, the more of the light you're going to be able to capture. This is a picture of a complex of observatories, one off in the distance there, several that are here. We have the Very Large Telescope being built currently. That mirror that I showed you before with the very smooth polish on the top is being built here. We also have the Extremely Large Telescope, which is being built in a similar area. Over here, back in the distance, we have the visible, so Roy G. Biv, as well as infrared survey. So this is high enough up that it can get some of the infrared ranges that tend to be blocked by the atmosphere as well. One of the great telescope refiners and inventors in the 20th century was Hale. He's the one who built that 40-inch Yerkes Observatory in Chicago. Then he went west, young man, as they say, and built various others, including the 200-inch Palomar Observatory telescope, which for a long time was the premier instrument on the planet and the largest telescope in the world. But notice it kept getting bigger and bigger and bigger. But at this point, these all became reflecting. So 40 inches is maxed out for refracting, and anything larger ends up being the mirror. The other thing that's useful about mirrored telescopes like this is the weight is in the bottom. It's not in the top swinging around. And that can make a lot of engineering differences. But some things, again, had to wait for other technologies, because when we're looking at things even through Palomar or even through the Keck, there are problems with the atmosphere. We now use adaptive optics, which are a range of different kinds of technologies, so that we can get clearer images with our ground-based telescopes and get some of the wavelengths we might have been missing out on. This is an infrared picture of Jupiter, for example. When we're looking at these kinds of pictures, we're taking actual pictures from the telescopes. We don't tend to use film too much anymore, not just in terms of what you and I do, but in terms of what astronomers do. We use charge-coupled devices. You have a charge-coupled device. If you have a cell phone with a camera in it, you're using a charge-coupled device. What happens here is the pixels are responding to the photons that are coming through and hitting at a certain energy, at a certain wavelength. And it will say, okay, this was green, this was blue, this was red, this was aqua, this was whatever along the way. And the more pixels you have, the better the resolution you're going to have. As you may have discovered, if you're working on the internet, you find a picture and you want to blow it up and then it becomes fuzzy. But if you have more pixels, it doesn't have that fuzziness. So if you have standard definition or high definition or ultra high definition, other kinds of things like that, the more pixels we have, the better we're going to get. But there's always going to be an upper limit. When we're looking for different types of waves, here with our guy holding the trash bag, this is Roy G. Biv, but when we're looking at it here, it looks like his soul has disappeared because the glass in his eyeglasses is actually blocking some of the light that's coming through. We can see he's much hotter than the rest here. His clothes are probably closer to room temperature. His body is probably 98.6. We can see through the bag because the bag itself, again, is at room temperature, and his hands are 98.6. So we can see through it using the infrared. When we bring our light through the telescope, it helps if we can then put it through different processes, including prisms, and we'll take it through a prism and we can break our images into different types of coloration and different types of data that we get. We are always looking for how much we can distinguish. If you look at Jupiter with the naked eye, And you can actually do that tonight, June 21st. If you go out sometime, if you're watching this video in 2020, in the summer of 2020, and you go out in the early morning and look towards where the sun will come up, you'll see a very bright dot. That's going to be Jupiter. And Jupiter, with the naked eye, looks like a dot. But if you go out, even with low-powered telescope, you can actually see 2, 3, 4, as many as 5 dots around that dot, because it's resolving it more. It's taking those lights and spreading it out. That's resolution. The higher power telescope you have, the more you can resolve. We can also use different kinds of technologies, sometimes oil coatings, for example. Remember, oil is good for refracting light. We can use that in different ways. I have lenses that have different oil coatings on them, so I can see in different ways. Our upper limit to that is called the diffraction limit. So even if we have the best telescopes in the world, like the Hubble, some things are just so far away that we're going to get pixelated. And that's what's happening here with this image. So here we can see what one of the benefits of breaking it into the different colors. We have blue and green and red. If we're looking at it all together, we might miss the fact that there's blue all behind the red. We can miss the fact that there's green throughout the entire thing because it's been sort of obscured and absorbed. The red is in the front, but this structure, this sort of cloudy kind of molecular structure, molecular clouds or dust clouds that are there, tend to be a sort of a portion of the green filter that's there. And we might not realize that that's not really part of the red if we weren't looking at it in that way. And what we can tell in part from this also is that this is a three-dimensional thing. We've got blue, which is higher energy, feeding into the red. What's happening, of course, is it's sort of cooling off in that direction. Green is between Roy, which is lower energy, and Viv, so it makes sense that that would be a transition kind of color. This is a three-dimensional thing. This is an X-ray. Again, you can't see X-rays. You can't see X-rays directly. But what's happened here, if you were going through the Starship Enterprise and coming up on this and just looking out your window, it would look empty. It would look blank. This is not what you would see with the naked eye. What they have done is they have taken the X-ray image and again transposed it down to Roy G. Viv. But when you do that, you still have lower energy showing up in red, higher energy is showing up in blue, mid-range showing up in green. Radio waves are also invisible to the naked eye, but we pick them up with radio antennae and other kinds of things. Here's a guy named Jansky. We still talk about the power of radio signals in Janskys after this guy here. If you have something in wattage, like a light bulb is a certain kind of wattage, 100-watt bulb, 40-watt bulb. There's a guy named Watt. There was a guy named Ohm. There were guys that we name our units after people quite frequently. When this was first being built, one of the apocryphal stories is that someone thought this was a new way to dry clothes. You would hang clothes up here and spin it around, and that would dry clothes. This is a radio antenna. It's a rotating radio antenna. If you think about what a radio antenna is, you think about it on your car. If you've got an old-fashioned car, it just has the metal bar that goes up and down like that. That's all it takes. If you have an old-style transistor radio and you pull out the antenna and it goes up, that's all an antenna is. That's what a radio telescope is as well. You're just tuning in to different ways of looking at things. But radio telescopes can break the bank. Here's Green Bank telescope, no pun intended. Robert C. Byrd Green Bank telescope. If you become a senator somewhere and get funding for something like this, you too can put your name on it. This is one of the major steerable radio telescopes in the world. It is a huge thing, 100 meters across. Think about 100 yards is a football field. That's what this is up here along the way. This is in West Virginia. Then we have some multiple setups. This is the Atacama Desert Array called the ALMA Array. And these radio telescopes work in concert with each other. Even if I didn't know this was the Atacama Desert, I would know it's a southern hemisphere picture. Why would I know that? We've got these little fuzzy patches over here, large and small Magellanic clouds. You can't see those from up here in Indiana. And then we have the Very Large Array. If you've seen the movie Contact with Jodie Foster and Matthew McConaughey, part of it takes place here. These are steerable, and you can chain them together. So if you're looking at the same thing through all of them, you can simulate through a process called interferometry, having one large disk the size of all of these put together. Then we have this one, the Arecibo, and this also features in that movie, Contact. It also features in GoldenEye with James Bond. So if you sort of go back and watch that, this is a dried up lake bed. It is not steerable because it's caught where it is, but it's further to the south, so it can catch things widely north and south. And the top here is the part that is movable and steerable. So you can angle it somewhat under this kind of operation. This is not the largest radio telescope in the world anymore. There is a new one that's newly built in China. I'm not entirely sure if it is completely operational yet, but I do know that it went online just in the last year or two. These things take a long time to build. But as we're looking in radio waves, we can see things like this. Again, we have lower energy and higher energy areas. We have a center of a galaxy where it's pushing jets of energy out. It's pushing jets of material out in two different directions. So we sort of see that. This is probably close to twice as wide as our entire galaxy. So not just our solar system, not just our neighborhood in the solar system, not just our galaxy, but twice as much as our galaxy. So this is a huge, huge, huge area that's out there that's being sort of all of this stuff being shot out. So these kinds of things exist on the edges of our universe, which means they also exist in the early part of our universe. Remember, the further out you're looking, the further back in time you're looking. Here's where the Arecibo is in Puerto Rico. Here's where the Green Bank is. This is where the Very Large Array is. Notice we've got several other installations, including over here in Hawaii. What we can do is we can chain these together to look at the same thing and simulate having a disk this big. You can't do that too well with shorter waves. But remember, radio waves can be very, very long. So the longer the wave is, the more likely this kind of chaining together is going to be successful. Another issue we have with regards to where we build on the planet is this picture here. Notice Western Europe, very lit up. Notice Eastern United States, very lit up, and the West Coast, very lit up. These are not great places for observatories. This bright, bright, bright spot here, that's Chicago. That's where that Yerkes Observatory is. Not helpful, not helpful. This is where Mount Palomar is. Again, when it was built, Los Angeles had like 2 light bulbs, and now it's Hollywood. They beam light into the sky just for the fun of it. So when we're looking for places on the planet to not encounter too much light pollution, well, here's Hawaii. Again, the big island, you can barely see it here. Then we've got this area here, Chile. Again, dry, mountainous, desert, dark. That helps. The equator runs right about here. So when we're doing the equator right around here, Hawaii's just a little to the north, Chile's a little bit to the south. And we can cover the entire sky from both of those. We have some great observatory spaces down here in Australia, but again, from Australia, you're going to miss a lot of the northern sky. We have some very dark patches in Iceland, but you're going to miss a lot of the southern sky here. Plus, the weather's typically not too great in Iceland for building observatories, so no one's really done a lot of that yet. There are still scattered observatories all throughout Europe and all throughout the United States, but light pollution does create issues along the way. And it's interesting just to look at maps like this, pictures like this. You can see where people live and don't live and where technology is. You can see the Nile River here. And you can see exactly where the border from Egypt to Sudan is, because Sudan doesn't have the same kind of tourism or infrastructure that Egypt has. So the lights just sort of stop. We can see South Korea here, this dark patch above it, that's North Korea. So we can see the massive difference there. We can see Japan. You'd never want to build a major Roy G. Biv observatory in Japan because of all the light pollution that's there along the way. So we can see India with 1 billion people and China with 1 billion people are nowhere near as lit up as Western Europe or the United States, each of which have less than half of each of those places that are there. So it's interesting to look at these from a sort of sociological and economic perspective as well. How do we deal with that? Well, we can get away from the light and we can get away from the atmosphere by going above it. One of the ways in which we do that is with the SOFIA plane. It has an infrared astronomy instrument. So as it goes above the clouds and above the parts of the atmosphere that block the infrared, it can lock onto things. Then, as we're getting even further up, we can go and look at the infrared through the Spitzer Space Telescope. The Spitzer is one of what we call the NASA Great Observatories program. And it was in operation for a lot longer than it was supposed to be, for about 15 years. And its primary mission was meant to last like 4 to 6 years. So we really got a lot of stuff out of this. And I suspect that in the chronicles of solar system and outer space development, as well as deep space development of science, Spitzer will become more vital and famous than Hubble. And it just got decommissioned about a couple of months ago. So it's not actually that old of a piece of technology. But what it did was it opened our eyes to so much that's out there that we could never see, even with the Hubble as it was originally constructed, because it is looking at things that are beyond our visual range, and we can pull what it sees down back to our visual range, and we can see the way in which stars die. We can see ways in which the universe folds back on itself in different interesting ways. Then, of course, we have the Chandra X-ray satellite. This is another one of the NASA Great Observatory systems. How do you catch an X-ray? If I send an X-ray to you, it goes through you. That's how we sort of see the skeleton and bones and other things. It doesn't get reflected back, and it doesn't get absorbed into like a photograph kind of thing. It just goes right through, and what's left over when you're looking at an X-ray, well, that doesn't really help us all that much. So this is a unique design that's here. What we do, instead of having the X-ray go right through, is you have to trick it. And we have a coil of mirrors so that as it comes in, it bounces and bounces and bounces and bounces, sort of like skipping a stone on a pond. You can just throw the stone into the pond and it'll go ploop. But if you can get it just right, it's going to go pop, 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 pop. That's what happens here. The X-rays are captured and they bounce their way down to the focus that's down there. So it doesn't focus nearly as well. In fact, the higher the energy, the shorter the wavelength, the less focus we get along the way. But that's especially true for the gamma ray telescope, the Compton Observatory, because it really doesn't give us any focus at all. It's sort of, you aim it in this direction, yep, there are gamma rays there. Aim it in that direction, nope, there are no gamma rays there. And we can isolate areas and we can look at intensities, but we can't really get focused pictures from the Compton. Again, Compton and Spitzer and Chandra are named for specific people. Chandra, in fact, was named for a guy named Chandrasekhar, and he spent a large part of his career sort of almost on the outside of astronomy, because when he was very young, he was sort of talking to the people in the British astronomical community. Sort of Oxford and Cambridge tended to be somewhat dominant at that time, and they poo-pooed his ideas. Oh no, oh no, no. Well, he eventually won the Nobel Prize, but it took like 50 years before they came around to figuring out, oh yeah, he was right after all. But again, here's our atmosphere, light coming through the atmosphere, gamma rays, X-rays, infrared often blocked, but we can get the Sophia plane up to a level where many of the infrared rays are caught. Visible light gets a little bit obscured. So if we go above the atmosphere, we can see things without any of this atmospheric interference. We don't tend to need that with radio waves so much. When we're looking at the Hubble in particular, because of course the Hubble is where it's at in terms of public identification of telescopes, especially space telescopes. Hardly anyone knows about the Compton or the Chandra or the Spitzer, which is too bad. Everyone knows about the Hubble. This is a picture that was taken, sort of like a time-lapse photograph, but notice the timing here, September 24th, 2003 to January 16th, 2004. What we did was we sort of aimed it there and sort of left it there and took it again and again and again and again and again. Let the image sort of build up so that we could see things that are as far as 13 billion light years away. Sometimes you have to do that. You have to focus on a dark patch and just sort of leave it there to see what will come. If you were looking at this patch with the naked eye, you would not see it. If you were to look at it through the Hubble with the naked eye, you would not see it. This is what comes from allowing the photons to accumulate over time. And this is a long time to sort of keep your eye open and look for such images. But the Hubble is up in space. It goes around our planet roughly once every hour and a half. It goes around roughly 17,000 miles an hour. It goes on an orbit that changes, so it's not always overhead at the same place. So you can sign up with NASA to see when it's likely to be over Indiana. It will always be towards the south, and it will always be hugging that area over there. It doesn't circle the poles. It goes in an orbit that keeps it equatorial, because again, if you're near the equator, you can see the entire sky along the way. It is solar powered. The solar panels will drift around to keep a lock on the sun. And the images that we've gotten back are spectacular. These are the pillars of creation. These are in the Eagle Nebula, and these are gas and dust clouds, which contain, and you can see a bit poking out here, hundreds of stars that are being formed by the gas and dust that's in there. This is a close-up of the Horsehead Nebula, which is an absorption nebula that's also going to collapse into stars and planets. Here are several images. This is the butterfly up here. And when we have this, we have different interacting. It looks like we have these two interacting galaxies that we're seeing here. We have this Carina Nebula. Again, the light that's coming out of the crevices of the gas cloud here are stars that have turned on inside and are beginning to blow the gases and dust away. And this is a colorful picture of stars, a star field in the globular cluster, which is a cluster of anywhere from like 50,000, 100,000 to maybe 1 million stars, just as a sort of compact unit that orbit our galaxy along the way. Blue means hotter, red means cooler in terms of the temperature signatures that are there. And then we have the James Webb Telescope. The James Webb Telescope is the successor to the Hubble. You can see these, it has that same kind of segmented mirror that we saw happening with the Keck. Each one of these mirrors is about the size of the Hubble's mirror, so you can see how much larger. There'll be another one down here as well. How much larger this is going to be compared to the Hubble. It's also going to be stationed considerably further away from the Earth to get away from some of the additional sort of noise and light and backdrop that's there. And then we have here the extremely large telescope, which is in planning preparation now to go along with the very large telescope that's already being built. These little shadowy things down here, these are people. So you can see just how large this mirror is. Here's the thing, this mirror here, when it's eventually built, will be able to capture images as good in quality as the Hubble is above the atmosphere. But that's like saying this thing here, just my little sort of circle thing, above the atmosphere takes something this big around on the Earth to match it. So the Hubble, in terms of size, isn't that large. It isn't as large as the Palomar. It isn't as large as this, certainly. It isn't as large as the Keck or anything, but it's in many ways better because it's above the atmosphere. We are making advances. Of course, it's been there for 30 years, and in 30 years, we've made advances so that many of the images we get from the ground are of equal quality, sometimes perhaps just a little bit better, depending on what we're looking at. But that's going to change as well when the James Webb Telescope goes up. Now, the James Webb Telescope is supposed to be up there next year or the year after. Here's the thing. It was supposed to be up there as much as 15 years ago, and it keeps getting delayed and delayed and delayed, and every time it gets delayed, there's also a cost overrun. And the last time that happened, Congress said, well, maybe we're not going to fund it after all. That would be unfortunate because it's sort of like paying for 95% of a house and then not buying the key to unlock the door so you can move in. So I'm very hopeful that it actually goes up and is successful. But because we don't have a shuttle that can go up and fix it, it needs to go up and work right the first time, and that's what it's taking some time. I'm going to pause the video here for a moment so that I can show you a couple of different things. One of which I will change my background here since we're talking about the James Webb Telescope. There we are, ta-da. Notice how shiny that mirror is. You can see the person working in the mirror. You don't quite think of this as being a mirror, but in fact it's reflecting what it's seeing. That's not the surface of the mirror that you're seeing as much as you're seeing what it's reflecting. I'm going to pause here because I want to find an infographic that I want to try to share with you. Okay, I found the infographic I wanted to share with you. So let me see if I can share my screen one more time here. And let me see if I can go to enter full screen. Will it let me do this? Yes. Here is a depiction of the different sizes of mirrors that are out there when we're looking at the different kinds of mirrors in our reflective things. Here's a basketball court. Here's a tennis court for size comparison. This image down here in the lower left-hand corner. Let me see if I can bring on our annotation. This is the Hubble. Notice this tiny little mirror here. That's the Hubble. That's the Hubble mirror. Notice the Keck up here. Notice the twin mirrors of the Keck. They dwarf the Hubble telescope. They dwarf even the James Webb telescope, which will be much, much larger with many, many more segments to it than the Hubble, which is just one mirror that's there. The Very Large Telescope, and I showed you that mirror being crafted, is several mirrors down in Chile. The Very Large Telescope is going to be dwarfed by the Extremely Large Telescope. That's also, even though it's being developed by the Europeans, is going to be based in Chile. The 30-meter telescope is the one I talked about being the sort of controversial planned one for 2027. I'm going to guess we're going to look at 2030 at the earliest time for that one. We have this one as planned. It says 2025. I'm going to push that one back some years as well. And the Giant Magellan Telescope, also in Chile. Again, when you find a place to build, you keep building there because you know it's good. Also, all your neighbors are doing it too. If you have an issue, you can go down the road and there are other people who are there. The sort of fraternity and sorority of the people who do this kind of stuff is actually pretty small in the world, and everyone tends to know everyone else fairly well, if not directly, then by reputation. Going up to the older telescopes, here we have the Yerkes Observatory one up here, this little circle that's there. Notice how small it is just compared to the Hubble. Notice how small the Hubble is compared to the James Webb. Notice how small the James Webb is compared to the Keck. And then we get, oh my goodness, over here, all of these things. But we have these, like the Hobby Eberly telescope. We have the South African Large Telescope. They're in operation now. We have the Grand Canaries on the Canary Island Telescope. That's in operation now. So we have several of these larger ones that are already in operation. These mega ones over here are still in the planning or the building stage. And the James Webb, as it says, planned 2021. We hope that's there along the way. But notice these up here, over or down here, I should say, the Gaia and the Kepler and the James Webb and the Hubble. This James Webb Telescope here will do as good, if not a better job than these big three ones here. And that's what happens when you can get rid of the atmosphere and get rid of the interferences that we have. But with increasing technologies, when we have this one on Earth, if there's a problem with it, we can fix it. If there's a problem with this, we're out of luck. If we change our technology 10 years from now, which is entirely possible, we can adapt this one. Again, this one, we're out of luck. When the Kepler failed, it failed. We were able to extend its life for a couple of times. The same was true with the Spitzer telescope as well. But eventually, they wear out in ways that some of these on Earth, the Hale Mount Palomar telescope is still in operation. And you can see it saw its first light in 1948. The Yerkes Observatory was in operation for more than a century, far more than a century, sort of a century and a quarter before it got shut down along the way. So things on the ground are typically going to last a lot longer as well than things in orbit. But 30 years in orbit, that's not bad along the way. So I wanted to share that with you so that you could sort of see what we're talking about, how big is. In terms of really big things, this thing behind me, not so big. But I will see you for our next lecture. Stay tuned.